The next topic we're going to talk about is converting equations between the two different systems, rectangular equations and polar equations, that is. Now, the idea is very similar to converting points. We'd still use the same transformations. So, x equals r cosine theta, y equals r sine theta, x equals the square root of x squared. R equals the square root of x squared plus y squared, and theta equals the arctangent of y over x. We use these transformations within these problems. So let's look at our first one. R equals 4 sine theta. Now, students will often see the sine and say, this is the transformation I want to focus on, which is correct, okay? But the thing is, you can't directly transform 4 sine theta into y. And the thing is, you have to have the variable r here. Students will think they see the 4 and they're like, oh, okay, well, r just equals 4 in this case. But that's not how this works. It's a transformation of the variable r times sine theta transforms into y. So we can't just translate that into y directly. There is two different things we can do here to adjust. One method is to multiply both sides of the equation by r. And what that would do is introduce an r, and then you can directly translate. So that's fine. I'll do that in another example, but I think what most students attempt to do is something like this. You see, these formulas over here, you don't have to use them at face value. You're free to manipulate them. So for instance, I could take the one highlighted and I could say that sine of theta is y divided by r. And that's perfectly fine. Then I would have r equals 4 times y divided by r. I can directly translate that. I still need to do the step of multiplying both sides of the equation by r, however. I don't actually get away from that. So r squared equals 4 times y. And r squared, I would use the next equation here. But in this case, I wouldn't use it directly. I would transform it to where I have r squared. Let me write that out. R squared equals x squared plus y squared. All right, so then this becomes x squared plus y squared equals 4y. Okay, now, as in terms of a rectangular equation, that's perfectly fine. That is the rectangular form. If that's all you need, that's okay. But some questions might ask you, like, what type of curve is this, and some other metrics. So one thing you would want to identify is there's 2 squared variables, which means that this has to be a circle of some sort, or possibly an ellipse. Well, actually, maybe one of the other conics as well, but most likely a circle. To identify it, it is kind of like this is written in general form, and you would have to translate it into standard form. All right, and we use complete the square to do that. So if I take this number here, multiplying my y, divide it by 2, that's -2, and square it. And add that value to both sides of the equation. So I would have x squared plus, this then factors into y minus 2 quantity squared equals 4. So now I know that this curve is a circle with a center at 0, 2, and a radius of 2. So the center is the x and y transformations, so the horizontal shifts and vertical shifts on the x and y variable. Just take the opposite of the signs listed, and the radius is the square root of this constant value. All right, let's try the next one. So here I have theta equals pi over 3. And in this case, I can take advantage of this equation right here. Now, no one likes to work with that one because of the arctangent, and they just kind of shy away from it. It's generally not that bad to work with, though. You can just directly transform theta into arctangent of y over x, and then that would be equal to pi over 3. And that's really a fine rectangular equation that meets the criteria of being rectangular, but if you want to know what kind of an equation this is, it's not really going to be quite evident. But it's easy to find out. We just need to do a little bit more manipulation. So for instance, I could take the tangent of both sides of this equation. And if I took the tangent of arctangent, I'm just left with y over x, and then I have tangent pi over 3 here on the right-hand side. Tangent pi over 3 is one that you should recognize, or at least could do sine of pi over 3 over cosine pi over 3. What that results in is the square root of 3. And if I multiply both sides by x, I get y equals the square root of 3 times x. And that's a lot more evident that we have the equation of a line here. Next up, I have r equals 3. Well, there's not much to do, but I do know that r is the square root of x squared plus y squared. And if that's equal to 3, then, well, already I've got a rectangular equation. But it's probably a little bit nicer looking if I went ahead and squared both sides and wrote this in the form x squared plus y squared equals 9, because then it's a little bit more evident that this is a circle that's centered at the origin and has a radius of 3. All right. This next equation, I have r equals 6 cosine theta minus 8 sine theta. It's very similar to the first. I can't directly translate for sine and cosine just yet, though I could do something like I did in that first example with x over r and y over r. But I'm going to do a different route this time. I'm going to multiply everything through by r first. And what that does is it changes the original equation in such a way that I can directly transform. And you're free to do either. I'm just introducing both methods just in case you prefer one over the other. But r squared can transform into x squared plus y squared. And then r cosine theta would be x, r sine theta would be exactly y. And in order to identify what type of curve this is, it's in a general form. We need to change it into more of a standard form, and we would do that by, again, completing the square. So right now I have x squared minus 6x, I'm going to leave some space for the x's, then y squared plus 8y, and leave some space for the y's, and complete the square. So the negative 6x divided by 3 would be 2, or sorry, divided by negative 6 divided by 2 would be 3, 3 squared would be 9. So I'd add 9 here and here. 8 divided by 2 is 4, 4 squared is 16, and then I would add 16 there. So this becomes x minus 3 quantity squared plus y plus 4 quantity squared equals 25. And this is a circle, and the center of this circle is at 3, negative 4. You take the opposite of those signs there. And the radius of this circle is 5. That's the square root of that constant over there. All right, let's go the other direction, see how that can be done. So we have some rectangular coordinates, and we want to write them in polar form. So first off, x squared plus y squared, if we think about this transform right here, r equals the square root of x squared plus y squared, it gets a clue as to where we'd want to go. but it's probably better if we square both sides of that equation. And then we can directly transform this for r squared. And that's equal to 4. And to get r by itself, that's what we want for a polar function, is r by itself. So just take the square root of both sides. And you could do the positive negative square root, but it actually doesn't make a difference here because the way that polar coordinates just basically remap themselves for negative radiuses. So, or radii, I should probably say. All right, so r equals 2. That's the same equation. Lastly, x plus 2y equals 4. So I know that x can be replaced with r cosine theta. Y can be replaced with r sine theta. And that's a perfectly fine rectangular equation, but it should be a form where r is by itself. So let's work on that. So first thing I notice is there's a common factor of r in each of these two terms. So I can pull that out, and then that leaves me with something that I can divide to the other side, and I would have r by itself, and then 4 over cosine theta plus 2 sine theta. And that was a line, so this would be the equivalent of a linear equation in polar coordinates.